Hello and welcome to our lesson on polynomial inequalities. This is going to be from section 8.6 in our text, and we have a brief introductory list of instructions we're going to go through, and then we'll jump into the examples. So, step number one, when you're solving a polynomial inequality, you need to make sure that one side is 0. It doesn't matter which side. I prefer the right-hand side to be 0, but that's going to be up to you. Second, once you've got one side equal to 0, then you're going to set your polynomial equal to 0 and solve, and that will get your critical points. So to solve the polynomial equation, depending on whether it's quadratic or cubic or whatever, you're going to use an appropriate technique to find the solutions and give your critical points. Then you'll take your critical points, put them on a number line, determine whether those points have open circles or solid dots, and then you'll come up with test points. And the test points are used to determine the solution intervals. That's going to give you the interval notation for the solution set of the polynomial inequality. So now we need to jump into the examples. Our first example, number 29, here we have a quadratic inequality, and I can tell it's quadratic because the biggest exponent on any variable is 2. Step number 1 is to make one side 0. So in a quadratic, you really want that x squared term to be positive, so I'm going to bring the x and the minus 2 over, and that will make the right-hand side 0. So when I bring the x over, it makes it minus x. Negative 2 becomes plus 2. Those are now gone, and so this is now greater than or equal to 0. So I'm going to have x squared minus 2x minus 3 greater than or equal to 0. And I believe this is going to factor, which is the fastest way to solve a quadratic. So I'm going to solve by factoring. Remember, to solve a standard trinomial, you start with parentheses and then read the signs. These signs are going to be opposite. Last, we fill in the blanks, x and x to make x squared. And I need numbers that multiply to make 3, that subtract and make negative 2. And that is going to be 3 and 1. Notice the 3 goes with the minus because I do need minus 2. 1 minus 3 is minus 2. Negative 3 times 1 makes negative 3. So that is factored correctly. And then I'm going to set each factor equal to 0 and solve. Remember, I'm setting them equal to 0 because these are going to give our critical points. So moving the 1 over gives me x is negative 1. Bringing the minus 3 over gives me x is 3. Now that I've got my critical points, I'm going to go to the numbered line with my critical points. And I need to know if these are going to be open circles or solid dots. That is based on your inequality. Since it has the equal to part, these are going to be solid dots. Now I need test points. And you do need a test point for each region. So in the first region, my test point has to be less than negative 1. I'm going to jump all the way to negative 5. It doesn't matter what you pick, as long as that value is in the region. I next need a test point between negative 1 and 3. I'm going to choose 0. 0 is a good test point anytime you can use it. And then last, I need a number bigger than 3. I'm going to go positive 5. At this point, I've got my 3 test points, and I'm going to plug them into the factored version of the inequality because it's easier to check there. So starting with negative 5, we're going to replace every x with negative 5. And then what I want to know, does that work out to be greater than or equal to 0? Well, negative 5 plus 1 is negative 4. Negative 5 minus 3 is negative 8. And a negative times a negative makes a positive. Now, I don't really care what it is since it's going to be greater than or equal to 0. I just need to know if it's positive or negative. Positive numbers are greater than or equal to 0, so that gives me a true statement. And you do shade the true parts. So that means this entire region is going to be shaded because that test point determined that that was true. Next, let's test 0. Again, replacing each x with 0. And then we're going to calculate to see if it is indeed greater than or equal to 0. 0 plus 1 is 1. 0 minus 3, negative 3. A positive times a negative makes a negative. Negative numbers are not greater than or equal to 0. So that gives me a false statement. And last but not least, we need to check the 5. Positive 5 replacing the x's. And then is that greater than or equal to 0? 5 plus 1 is 6. 5 minus 3 is 2. 6 times 2 is 12, which is positive, which is definitely greater than or equal to 0. So that also gives me a true statement, which means I'm going to shade that region. Now that I have each region shaded based on whether it's true or false, I can now write the solution set in interval notation. So what is shaded? Well, everything from minus infinity up to negative 1. And we're going to use brackets because we had solid dots. And since there's a gap in between the shading, we need to use the union symbol. Remember, the U is the glue that sticks the two pieces together. And then the shading picks up at 3 and shades to infinity. And so this is going to be the solution set for this polynomial inequality. Next example, number 39. This time we have a cubic inequality because the biggest exponent is a 3. Step number 1 says we need to make one side 0. So I'm going to bring the 15x over. That'll make the right-hand side 0. And that'll give me 4x cubed minus 7x squared minus 15x less than or equal to 0. It is better if you write your polynomial in descending order. That's just good math etiquette. Now, to solve this polynomial inequality, I'm going to again solve by factoring. Notice that each term has an x, and so the first thing I'm going to do is I'm going to factor out an x. That's going to leave me 4x squared minus 7x minus 15 less than or equal to 0. So at this point, I have two factors. It's not factored completely because here I still have a quadratic factor. And since this quadratic has a lead coefficient, if I'm going to try to solve by factoring, I'm going to use the 3R method. So if you're not familiar with how the 3R method works, here we go. The first R says to remove. We're going to remove the 4 and multiply it by the 15. Now this first factor of x has to come down. The 4 got removed and multiplied by the 15. Now what that does is it turns my trinomial into a standard trinomial, which is much easier to factor. So to factor a standard trinomial, we're going to use our parentheses and then read the signs. These signs have to be different. And then fill in the blanks. X and x to make x squared. I need numbers that multiply to make 60 that subtract and make -7. Are there numbers that multiply to make 60 that subtract and make -7? Well, that's going to be 5 and 12. Okay, check me. 5 times 12 is 60. -12 plus 5 is -7. So then that is factored correctly, but it's not factored completely. Remember, we're doing the 3R method. So the first R says to remove. Now the second R says replace. So whatever I removed, I now have to replace in front of each X. And the third R says to reduce. So in the first set of parentheses, can I reduce 4 and 5? No. So that's going to come down. In the second set of parentheses, can I reduce 4 and 12? Yeah, those are going to reduce by 4. And that's going to leave me x minus 3. And so then if you want to check that, you can do the FOIL method here and make sure we get that original quadratic back. But that is going to be factored correctly. Now it's also factored completely, so I can set each factor equal to 0 and solve, and that'll produce my 3 critical points. So for the first factor, x equals 0, that's already solved for, so that's a critical point. 4x plus 5, we're going to bring the plus 5 over and then divide by 4. My second critical point is going to be -5/4, and I'm going to leave that as an improper fraction. And we're also going to bring over the -3, which will make +3. So now that I've got my 3 critical points, it's time to go to the number line. I need to put these 3 critical points in the right order. So -5/4 is the leftmost, and then 0, and then 3. Now we need to determine if those are going to be open circles or solid dots. That is based on the inequality, which does have the equal to part. And so these are all going to be solid dots. And now we need test points. And you do have to have a test point for each region. So I need a test point that is less than -5/4. I'm going to pick -2. Now, it doesn't matter what you pick as long as it is less than -5/4. Then I need a test point that is between -5/4 and 0. I'm going to pick -1. A test point between 0 and 3, I'm going to pick, 2. And then last but not least, I need a test point that is greater than 3. How about 4? Okay, so do you see I've got 4 test points, and I'm going to plug those back into the factored form of the polynomial inequality because, in my opinion, it's a little bit easier to check if you plug into the factored form. So checking our -2 first, we're going to replace every x with -2. And once we have every x replaced with -2, we then need to work this entire side out, following the order of operations, to see if it is less than or equal to 0. All right, so here we go. We've got our -2 times 4 times -2 is -8. -8 plus 5 is -3. -2 minus 3 is -5. Is that less than or equal to 0? Well, a negative times a negative times a negative is going to end up being a negative number. I don't really care what it is. I know it's going to be negative is a negative number less than or equal to 0? Yes, it is. And so that's going to give me a true statement. And so I'm going to shade that region since it's true. Now, normally these regions will alternate. So I'm going to go ahead and assume that this will be false, this will be true, and this will be false. But it's not 100% guarantee that they alternate. But most of the time they do. So I am going to go ahead and do the work to show that it is going to alternate. Next, replacing every x with -1. That's going to give us -1 times 4 times -1 plus 5 times -1 minus 3. And we need to know, is that less than or equal to 0? Well, that's going to be -1 times -4 plus 5 is 1. -1 minus 3 is -4. Negative times a positive times a negative is going to end up being a positive number. Again, I don't really care what it is. It's going to be positive. Is a positive number less than or equal to 0? No, it's not. So that will be false. And then we're going to go ahead and check 2 and 4 also. So replacing every x with +2 is going to give us 2 times 4 times 2 plus 5 times 2 minus 3. That's going to be 2 times, let's see, 4 times 2 is 8. 8 and 5 is 13. 2 minus 3 is -1. Positive times a positive times a negative is going to end up being a negative number. Is a negative number less than or equal to 0? Yes, it is. And so +2 should be true, and it was. It was true. And then one more test point to test. 4 times 4 plus 5 times 4 minus 3. That's going to be 4 times 16 and 5 is 21. 4 minus 3 is 1. Positive times a positive times a positive is a big positive number. But is a positive number less than or equal to 0? No, it's not. And so again, that's going to be false. So they did alternate. And now that I have every region determined, I can write the solution set. So the solution set in interval notation is going to be everything from -infinity up to -5/4 with a bracket, because that's a solid dot. And then since there's a gap in the shading, remember I need to use the union symbol. The U is the glue that sticks the two pieces together. And then the shading picks up again at 0, continues to 3, and stops. And that is the interval notation that represents the shaded regions. This here is the solution set for this polynomial inequality. And the last example we're going to look at in this lesson, number 41, here we have another cubic polynomial inequality. The right-hand side is already 0, so that's step number 1 taken care of. This cubic polynomial does have 4 terms. And so in order to find the solutions of this polynomial equation, we're going to use factor by grouping. If you remember from your factoring lesson, 4 terms means factor by grouping. And within the first group, I see that they have an x squared in common. So we're going to factor out an x squared. That's going to leave me x plus 3. In the second group, they both have minus signs. So I'm going to factor out a -1, which means the signs will change. And again, if you remember factor by grouping, if you factor correctly, the stuff in the parentheses should match. If the stuff in the parentheses doesn't match, it either won't factor by grouping or you screwed something up, okay? Next step, factor by grouping says that for these two terms, I need to factor out the x plus 3. So that's going to leave me x squared minus 1. Now that's factored correctly, but it's not factored completely. Because see here, I still have the difference of two squares, and so this will factor further. To factor the difference of squares, we're going to have parentheses, we're going to have different signs, and we need to fill in the blanks. X and x make x squared. 1 times 1 is 1. Now this is factored completely, and so I can set each factor equal to 0 and solve. X plus 3 equals 0, x plus 1 equals 0, and x minus 1 equals 0. And moving each one of these numbers over is going to give me critical points of -3, -1, and 1. Now to the number line with my critical points. Please make sure that you put them in the right order. They have to be in ascending order from negative to positive. And then they need either an open circle or a solid dot. Based on the inequality, these are all going to be solid dots. Now, I need test points. And you will need a test point for every region. So in the first region, my test point has to be less than -3. Let's say -5. I need a test point between -3 and -1. Let's say -2. I need a test point between -1 and 1. Say 0. And then my last test point has to be bigger than 1. I don't know, how about 5? Remember, I've said that it doesn't matter what you pick for your test points as long as those numbers are actually in that region. And then I'm going to plug these test points into the factored form of the polynomial inequality because I think it's a little bit easier to plug into the factored form. Starting with -5. That's going to be -5 plus 3, -5 plus 1, and -5 minus 1. I need to know, is that greater than or equal to 0? Well, that's going to be -2 times -4 times -6. Negative times a negative times a negative makes a negative overall. Is a negative number greater than or equal to 0? No, it's not. And so that first region is false, which means that the next region will probably be true, and then false, and then true. Remember, I said about 95% of the time those are going to alternate, but you need to plug in to make sure because it's not 100% guaranteed that they do alternate. So next we're going to check -2. -2 plus 3, -2 plus 1, -2 minus 1. Is that greater than or equal to 0? Well, that's going to be 1 times -1 times -3. A positive times a negative times a negative. Overall, that's going to be positive. Is a positive number greater than or equal to 0? Yes, it is. So that is true. And remember, you shade the true regions. Now we need to test 0. 0 plus 3, 0 plus 1, 0 minus 1. Is that greater than or equal to 0? Well, that's going to be 3 times 1 times negative 1. Positive times a negative is a negative overall. Negative numbers are not greater than or equal to 0, and so that false is verified. Last but not least, we need to test 5. That's going to be 5 plus 3, 5 plus 1, and 5 minus 1. Is that greater than or equal to 0? Well, that's going to be 8 times 6 times 4. Positive times a positive, that's going to be a big positive number. Positive numbers are greater than or equal to 0. So that true is verified, and we're going to shade the true region. And now that every region has been determined, whether it's true or false, we can now write the solution set in interval notation. So where does the shading start? Well, it starts at negative 3, and then it stops at negative 1. Remember, we're using brackets because we have solid dots. And then since there's a gap in the shading, we're going to use the union symbol. Remember, the U is the glue that sticks the two pieces together. And then the shading picks up at 1 and goes to infinity. And that is our solution set in interval notation for this polynomial inequality. And that's going to do it for this particular lesson. So if you have any questions or comments about anything I've done so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.